All right, day 35, page 790. I'll try to do problems 24 and 25. I've thought about this a little bit ahead of time. You take, this is going to be an expressional manipulation. I'm looking at some of the key players here, the key equations. Ohm's law, delta V equals IR. F equals ILB, the force on a wire. And E, or delta V, equals BLV, that last equation there. Sorry, I'm trying to write small to get this all in. But once again, capital E or script E, EMF is delta V. Little v here is velocity, so we've got to be a little careful here. All right, so let me work through this. So the force that you're going to apply to the wire, let's start with this middle equation here, F equals ILB. Well, the current in the wire, well, let's actually go to Ohm's law. I is going to be delta V over R. I'm just going to play around with here and this and see if it works out. So that's my delta V. So if I take this middle equation, then it becomes the force applied to pull that wire, assuming there's no frictional force between the two wires. The force that you have to pull is overcoming the electrical energy you're generating as the current flows through that resistor. Hey, let's practice right-hand rule for a minute. Let's practice that. If you pull that wire to the right, okay, what happens to the force on a positive particle in that moving wire? So bottom line is the magnetic field is into the page. So I'm taking a little detour here. So if I draw that diagram, you have a magnetic field as indicated into the page. And as you pull the wire to the right, bottom line is you're causing positive particles. I know the electrons are the ones that are actually affected, but conventional right-hand rule, that would be the velocity of the protons. And if you use the right-hand rule with your index finger pointing to the right here and your middle finger pointing into the page, that means that the force on the positive particles will be this way, that's F. So the current will go yeah, that's consistent with Lenz's law because as you, which I could have done instead of what I just did, as you pull that wire to the right, you're increasing the amount of flux into the page towards the floor, and the current will be induced according to Lenz's law. This is another approach. The current will be, let's just take the bottom section of wire. The current will go this way in this bottom wire. Now I'm doing it totally separate than the right-hand rule I just did, because if the current goes that way in that wire, according to the simplified right-hand rule, you would have X over here and flux coming up like this on this side of the induced current, which is offsetting the increasing downward flux inside that loop. We don't care what's happening outside that loop. But yeah, the current would go counterclockwise by Lenz's law as well. So that's consistent with using the right-hand rule up here on the right and Lenz's law here down on the bottom piece of that wire. Current will flow counterclockwise as we pull that wire outwards. But in any case, that's the detour. Going back over here to the actual problem at hand, so plugging in here, we have F equals basically delta V over R times L times B. All right. I just plugged in for I. And now I'm going to plug in for delta V. In other words, delta V is this. It never really tells me what to have my final answer in terms of. I'm just going to see what happens here. If I plug that in for delta V, I end up with F. And let's kind of rearrange things. Do I not get BLV times L? Okay, I get B L little v, the velocity, that's what I just plugged in, times L times B divided by R. So if I simplify a little bit here, I get the force that I'm applying, or whoever's pulling on this wire, is basically going to be B squared L squared V over R. Now, what was I given in this problem? I was given B, L, V, and R. Yeah, so we have F in terms of the givens in the wording of the problem. So I believe we have what we need. It just says, derive an expression for F. That's our expression, B squared L squared V over R. All right, that's problem 24. I wish they would have been more explicit about, an expression in terms of, but it's implied in terms of the givens in the narrative of the problem. Now 25, it says with 24 in mind, show that this power is equal to I squared R dissipated in the lamp. Okay, and there's a couple of different approaches. I think one of the more direct approaches is to recall that average power is if you have a constant force times a constant velocity. Power is force times velocity. That's one of our power equations. If you have a constant force, constant velocity. So if we take the above equation in the circle and multiply by V on both sides, so on the left side you have FV, which would be power. This equation, a relationship up above here, becomes P, power, equals B squared L squared V squared, once again the V being velocity, over R. Now, okay, this is really kind of nice because you have B squared L squared V squared. Well, that's BLV, quantity squared. Let me write that down. That's BLV, quantity squared, over R. Well, BLV, if you look way up on the top here, is delta V. So in other words, I'm a little out of space here, so I'm going to go way over to the left. That means that P equals, well, delta V squared over R. And if you remember, well, I'll go back to Ohm's law again, delta V equals IR. Right, I'm not necessarily doing this the most direct way, but delta V equals IR. So if we go way up here, or just even think about that, that comes all the way down. It's going to be, if you do it now, P equals that IR quantity squared. So it's going to be I squared R squared over R. So it's going to be I squared R squared over R, which is indeed I squared R. That's what we wanted to prove. We wanted to show that the power dissipated is now I squared R. Sorry about kind of moving all around here, but I did manage to get it all on one page. So I've shown in stepwise fashion that the power dissipated is I squared R.